So let's go ahead and get started. Let me kind of remind you of where we are and where we're headed here. I'll start with this little diagram here that we got acquainted with a while ago. But as you probably recall, the first four chapters, which I call the kinematic chapters, were right here. I'll put a little circle around it. I'll even put here chapters 1 through 4 and say that's the connection between position, velocity, and acceleration, and that was our focus on the first four chapters. For the last couple of weeks, we've been working then with the next set, if you will, and that is what I would say going from describing motion to explaining motion. And so chapters 5 and 6 are right here. These were Newton's laws of motion, and particularly Newton's second law of motion. And so, as you know, we spent a lot of time, first of all, in Chapter 5, then we spent a lot of time in Chapter 6, and we looked at different scenarios. Now it's time to shift gears a little bit and look at Chapters 7 and 8. And as I said, 7 and 8 are woven together really tightly. They could almost make one giant chapter. In fact, I'm going to kind of maybe make that approach since we're a little bit behind on the schedule. I'll point that out as we go along. But in this diagram, probably the thing to say then is we're about ready to go on here to what I would say then a little bit off this linear path. And we're going to talk about energies. We'll talk about kinetic energy. We'll talk about gravitational potential energy. We'll talk about an elastic energy. We'll talk about heat energy. We'll even leave the door open for other energies that will show up in the future, but we won't talk too much about it. But as you might recall from your Physics 102 class, there is a principle called the conservation of energy. And so this is the beginning of our 3 conservational principles. I think I said at the beginning, and it's worth repeating, this whole chapter, or excuse me, the whole semester on mechanics is really Newton's 3 laws of motion plus the conservational principles. And so conservation of energy being the first one that we're seeing. That'll be followed next chapter, or next unit I should say, chapter 9, with conservation of momentum, followed a little later with conservation of angular momentum as we start to get things rotating. So again, our 3 conservational principles, well maybe I should say three laws, we've done those. Now we're off to our 3 conservational principles. And that kind of summarizes the whole semester. In fact, it fits that whole theme I've been saying. Physics is about knowing how to apply a few fundamental principles to explain a universe of phenomenon. And so we're not going to learn a whole lot of details. We are going to have to work out the details for every problem, and the problems can be kind of long because of that. But the actual basic principles themselves are not. I'll even leave the door open here because, as you'll see with the math, that energy can not only lead directly to velocity, but it can also lead directly to forces. And so we have a little more complicated web, if you will, instead of this linear diagram that we would say, hey, take all the forces, add them up, give the net force. From that you can get the acceleration. From that you can get the velocity. And from that you can get the position. It's not quite always that simple. Perhaps we could do energy. And so we could go forces which lead to energy, which then leads to velocity. And we never have to really worry about the acceleration or even the net force, for that matter. Or we could already start with the energy and go right to velocity. And so kind of pointing out that we can get to velocity either then through an energy mechanism or through an acceleration in Newton's second law. Once we get there, we can get to position. Or the other way around here. We can start with energy and from that get to forces. And so I think that's a kind of a good way to start here in terms of our energy and adding to our diagram that there's more going on in the world besides the forces. There's also this idea of energy. And so I'll put here that what we're about to cover here, chapter 7, introduces us to the idea of work, and from that the idea of energy. And then as we transition from chapters 7 into 8, the title of chapter 8 then is Conservation of Energy. And so you can see how those two chapters are tied together. And again, before today's over, hopefully you'll see that in great detail. But I'll start with the concept of work. And again, like everything we do in this class, the idea is to take your past physics course together with your past math courses and kind of integrate them together and get problems, and more complicated problems, more advanced problems than we have done before. And so I'm going to start off with this whole idea of work. I know that you guys covered it in Physics 102, and many of you others maybe in a physics course labeled other than Physics 102, but I'm sure it was the same here. And so let me just repeat the standard definition of work that you're familiar with. The work done by a constant force, and so maybe I'll even underline that, constant force, because now with calculus, it doesn't have to be a constant force. It was in your previous physics courses. But with calculus, we can add to that. So the work done by a constant force then is defined as a product. And you probably stated it as force times distance. It's a little more complicated than that, so I don't want you to forget that, but it's defined as a product of the component of the force in the direction of the displacement. And that's a lot of words right there. But let me put it all with one big underline, because when we said here it's a product, that means we're multiplying two things together. What are those two things? And that long description is just one of the two things. And it's so long it's easy to forget or miss what it is. But that is the component of the force in the direction of the displacement. And then, and, here's the second part of it, the magnitude of the displacement. And so I'll put a little underline there too and say, okay, there's our two pieces. And you can see that this is a force and this is the distance or displacement. Force times distance. But notice it's a bit more complicated than that. It's not just the force times the distance. It is actually how much force is along the direction of that distance. And again, a lot of you are shaking your heads, and good, because that's no doubt what you saw in Physics 102, something along these lines. That if I were to take, say, a box here, and the box then slides along the surface. And so the displacement vector, I'll use the R, is along a horizontal line. That doesn't necessarily mean we pulled it along a horizontal line. We could have been pulling it off at some angle theta relative to the displacement that it moved. But this first one right here that says, okay, how are we going to define the work? And of course, notice it's only by a constant force. So we've got to add to that. But just to review what you learned in 102, you learned that it would be the component of the force in the direction of the displacement. So in other words, if I write out this equation for work, and let me just use W for work, how much of the force is in the direction of the displacement? Yeah, we've been doing a lot of this since chapter 3. This would be the X component, right? And so I would say if I go F, whoops, I almost put sign. If I go F cosine theta, that right there, would then, if I maybe grab a different color here, and look at that force vector, but I can look at how much of F, and I'll use that little symbol parallel. How much of F is parallel to the displacement? That's what this is. This is F parallel. It is how much of the force. It is this whole phrase here, right? It is the component of the force in the direction of the displacement. And let me emphasize, it's the direction of the displacement. It doesn't necessarily have to be the x direction. If the object moves in the x direction, as in mine, then that's what it is, the x component. And so this is an easy one to write out first, the x component. And then, of course, the other thing is then and the magnitude of the displacement. So in this case, I would put the symbol r with no arrowhead over it. Okay. By the way, notice that I've taken really two vectors, a force vector, and I even should have put a little arrowhead over it to say there is a force vector and there is a displacement vector. I took two vectors and I got a scalar. I got a number. I got work. And so the component is just a number. The magnitude of the placement is just a number. And when you multiply those together, you get the work, which is just a number. And so I've really taken two vectors and combined them in a way to get just a scalar. Some of you will recognize that from math, because in a minute I'm going to put your math together with what you've been learning. And we call that a scalar product in our math course, or a dot product in our math course. And so let's put those together. And then you'll see that overall theme. And then we'll extend beyond the Physics 102 and the math that you've seen. But that, again, is the goal here, is to take your math that you've learned, to take your mathematics that you've learned, and put them, together in a bigger picture. Anyways, that's a good place to start, because that's our definition of work. And then you'll see in a moment, it's a very useful definition of work, very restrictive definition of work. It means that the definition then does not have to do with just force times distance. It is the component of the force. And that's why that extra cosine theta comes into play. And so that would be the work done by whatever object is pulling on this box. Let me just put here my hand, just for the sake of discussion. Let's say this was my hand pulling on it. Because there's more going on here than just my hand pulling on the box. What else have we been doing in Chapter 5 if we were to draw the free body diagram on this box? There would not just be my hand pulling on the box. What other forces would be here? Yeah, good. So I heard them all. Somebody said gravity, good. Somebody said normal force, good. And somebody said some friction. And so I'll pretend it's sliding along there, and we'll call it a kinetic friction. And I won't worry about the air resistance. Let's just leave that one off there. But there are other forces. So then I could go on to say things like how much work is done by, say, friction. How much work is, say, done by gravity? How much work is done by the normal force? I could even then add them all together and say, what is the net work that you get when you combine all the work done by the individual ones? And as you'll see, some are positive and some are negative. I would say the one by my hand. Would you describe this as a positive number or a negative number? Yeah, it's positive. Why would you say that?
Because we can determine that. Why not?
Okay, go on. How do you know it's positive, though?
Because we decided that to the right is going to be positive.
No, I wouldn't say that. What if I called to the right negative?
Then it would be negative work.
Would it?
No, it's magnitude.
I mean, I would say the force would be in the negative direction, right? So that would be negative. But doesn't it move in the negative? So if I multiply two negatives, don't I get a positive? Okay, so is it negative if I call to the right negative?
No,
It's not, is it? So whether the work is positive or negative has nothing to do with my coordinate system. And I'm glad you bring that up, because that's one of a couple things I want you to see. But the work done by my hand is definitely a positive number. And it's not just because I'm calling to the right positive. If I call to the right positive, that's positive and that's positive. You multiply together, it's positive. If I call to the right negative, well, that's negative and that's negative. You multiply that together, you get a positive. And of course, what I really want you to see is I've got a positive times a positive times a positive, or I have a negative times a positive times a negative. And you notice I'm focusing on the angle there. Because regardless of which way I call positive and negative, these are the same signs, but that one perhaps is not. When would this number ever become negative?
If the force is not in the direction of the actual movement, displacement.
Well, I'd say the force is not in the direction of the displacement. Okay, so go on. So you mean the angle is greater than 90 degrees, right? That's when the cosine becomes negative. All right, so again, I would say that right now I have work that is positive. And in this case, I would say that because this one is positive and these other two are either both positive or both negative. Usually to the right we call positive. So I would call all these positive. And I'd say, yes, the work is positive. When could I get a negative work? That angle is more than 90 degrees. So let's talk about the work done by friction. What do you think I'm going to come out here? Think this will be a positive number or a negative number? Yeah, it's going to be negative. Why?
About 3 negatives in your equation.
Yeah, I will have one direction, say the direction it moves, and let's just call that the positive direction there, right? And then, if you take the magnitude of the force or magnitude of displacement, however you want to look at that, you could say both of these are positive. But it's that angle right there that is going to give me a negative number. And maybe I should have been more clear with the math. I should have probably said, how do they describe it? Yeah, the component. If we should put magnitude of the component, we could, because if we're going to put magnitude here, oh no, I guess I do like this because he doesn't do the cosine of the angle. I'm the one who changed it. All right, so I changed it to component here, but I guess still then what I mean is this is magnitude and then multiplying it by the cosine. But the point I'm trying to get at here is that we can have positive and negative forces. I mean, work. And be careful then and keep your eye on the positive and negative. Positive then, as we will soon see, comes from when the angle is less than 90 degrees, and what that does is tend to make our objects go faster. But we also have other work which can come out to be negative. That occurs mathematically when the angle here is more than 90 degrees, and that tends to make our objects go slower. And so you'll see as we keep working on the math, we'll have something called the work energy theorem, and we'll begin to see positive work makes our objects go faster and negative work makes it go slower. And I should say net work altogether, because when you have multiple forces, like in this case, one of them, like this one, can be positive, and this is the one I want you to see. This one is going to come out to be negative. If I wrote it this way, F sub k times the cosine of 180 degrees times r. Why the 180 degrees? Again, which way did it move? That way. Which way is the force of friction? That way. So what's the angle between those two? 180 degrees here. And so cosine of 180 degrees is kind of a nice one to work with. It's got a minus sign that I can just pull right out. And so again, maybe being a little more mathematical than we did in our Physics 102, since we didn't do too many trig functions, let's again take this whole idea of work from our 102 class, and then let's add to it. Let's talk about the component of it, but let's write it in terms of its trig function, and in this case, cosine of the angle between them. And that's, I would say, a step up from what we did in our 102. But it also then hopefully adds to your mind of, okay, that can be positive and that can be negative. Oh, let me keep going. How much work is done by gravity? 0. Why?
Cosine of 90 degrees.
Yeah, using our, I'll say, newer than the Physics 102, I would say the angle here is 90 degrees. The object moves along the x-axis. Force of gravity is down. There's a 90-degree angle. Cosine of 90 is 0. Coming back to our Physics 102, and we'll see that there is no component of the force of gravity in the horizontal direction that it moves. And so that component is 0. And so back in 102, you would have said it was 0 because it has no component in the x direction. Putting some more math with it, we would have said it's 0 because cosine is 90 degrees. How about the normal force? How much work is done by the normal force? 0. Why? Yeah, exactly the same argument, right? Cosine of 90 degrees. Or going back to our Physics 102, there is no component of the normal force in the x direction. So it moved in the x direction, but the normal force was in the y direction. And of course, now you can add those all together, and if you do, you will see that I get an F cosine theta times r there. And down here, I get minus force of friction times r. And probably not a surprise, if you look real closely at this, you will then see that this, once you factor out an r, is the net force in the x direction. Or put another way, it's the net force in the direction that it moved. And so the net work would be thought of as either A, adding up the work done by the individual forces, that makes sense, hopefully, but also it is equal to the net force times the distance it moved. And as you will soon see, there's a lot of usefulness in knowing the amount of work and the net work. Of course, I haven't showed that to you quite yet, but I just wanted to bring that first step up here, is that you guys have already done the concept of work from your Physics 102 class, and so let's just kind of expand on that. And in this case, so far, I would say the only expansion I've done is to say, let's add a trig function into it, since that's how we get the component, is by taking the trig function. But we see then, hopefully we see where we're headed with all of this. And in fact, let me pause for a moment also and add some more mathematics. Besides the trig function here, let me put then what you may or may not have learned in your math class, what we call the vector scalar product, also referred to as the dot product. And maybe I should ask you guys, in your math class, what name are you more familiar with? Dot product? All right, so maybe I'll keep referring to it as the dot product. I do happen to like the name vector scalar product because it does say exactly what's going on here, that we are taking two vectors, force and displacement. We are then going to multiply them together and get a scalar. We are going to get just a value of work. And so names aside, I'll stick to what you're more familiar with, the dot product, and said, let's kind of review this dot product that you may have seen already in your math class, you may have done something like this, that if you take two vectors, let's say this is vector A and this is vector B, and they have some angle between them, the dot product is defined this way, that if you take vector A and you dot it or multiply it by vector B, and maybe now's a good time to pause and remind you, remember what we did in chapter 3. We learned about vectors for the first time, the I-hats and the J-hats and even the K-hats. And remember, we learned how to add and subtract. We did not learn how to multiply. And at that time we said we're going to need to learn how to multiply when we get into chapter 7. Well, here we are into chapter 7. In fact, we're going to need to learn how to multiply two ways. One of them is a dot product, and the other one is a cross product, if you're familiar with that name too. We won't need that for a couple chapters, so we won't talk about it in this chapter, but we do need this dot product here. And the dot product's really quite simple. Usually in a math class, you just call that C and say, this is how we would write a dot product. And here's what we mean by it. What we mean is you take the magnitude of the first vector A, and maybe I'll put it in the order that you probably saw in your math class, and then you put the magnitude of the second one, B, and then you multiply by cosine of the angle between them. And so that's a nice definition, and you can just follow it. To give you some kind of conceptual feel for it, a lot of times we then draw these pictures and say, what really is A combined with cosine of theta? Well, if you take vector A and you look at vector A as made up of two pieces, oftentimes we label it as A parallel, meaning how much of A is parallel to B. In a math class, you might even have used the word the projection of A onto B. So how much of A is projected onto B? We could also talk about how much of A is perpendicular to B. That won't be important for this chapter, but in the future it will be. So I'll mention it now. But in our case, we would be interested in how much of vector A is in the same direction as B. And that is what A cosine theta is. And then you're multiplying it by B. So you're taking how much of A is then projected onto B, and then you multiply it by B. And isn't that exactly what we learned in Physics 102 for the definition of work? And so you can see, other than our mathematics is more advanced than we did in 102, we're talking about the same thing. We're talking a little bit of a formula here that is really writing this in terms of a vector. And so I would say I should go one step further and write work not in this form as I first did, but write it as a dot product. Write it as F dot R. And so, again, just kind of get us starting here with this chapter and what is work. I think you already had a good idea of what work was, again, from your Physics 102. But you didn't do as much math with it as we are about to in this chapter. And I think you see that already. Already I put in the cosine function. I've even went beyond that and wrote it as a dot product. Although I wouldn't say there's much change between writing it this way, because what that really means is the same as that. In fact, as you'll see when I start to do problems, probably the first thing I will do is to write the F, the R, and the cosine of the angle between them. And just say, okay, well that is what we mean when we write out a dot product anyways. Well, let's keep going with this, because I'm hoping you are seeing here that this right here is a nice mathematical way of writing out this definition of work. It gives me the two things multiplied together, one being the component of the force and the direction of the displacement, and the other one the magnitude of the displacement. Okay, perfect. But if you'll notice, this is the work done by a constant force. What if I don't have a constant force? Then what?
Take an integral.
Good. And now I'm going to put some more mathematics. Some mathematics that we did not have when we started 102. But you guys do have now. And I heard somebody say it, we'll do an integral. Yeah, let's prove that to ourselves. You probably did a number of these integrals in your math class, but let's say you hadn't done it. Could you come up with the idea on your own? Could you think through the problem? Oh, watch this for a moment. What if I were to take and make a graph that is force and the displacement? And maybe we'll come back to here. So here's this person grabbing the box with their hand, pulling on it. And so long as they always pull with the same amount of force, then everything we've said is perfect. However, that seldom happens. It doesn't always get pulled on with the same amount of force. The force does vary a little bit. And so maybe it's something like this. Maybe somebody starts to pull it across the room and they actually pull maybe for a little bit with a constant force. They grab it and they pull, but not to be a surprise, it maybe drops off. And they start off with a lot of ambition, if you will, and then they pull and they get a little tired. They realize, though, as they're not pulling as much, the box is beginning to slow down, and if they don't change, it's going to come to a stop. So maybe they pick it up a little bit, maybe they go back, and then maybe they get real excited they're at the end and they kind of finish the whole process. And so maybe they finally move it across the room or whatever they're trying to do here. But I'm just trying to give you some kind of silly story that most likely forces are not a constant. And so what are we going to do in a scenario like that? Well, you guys are, as you pointed out, familiar with calculus. And if I were to make this on a microscopic view or an infinitesimal view, I might say from here to here, the object did not move far. I'll just call it a little delta r. But I think it would be fair to say that between those 2 points, the force is roughly a constant. And if it's not quite a constant, make your delta r smaller and smaller and smaller and smaller. And so you're getting to see the idea that the work then would be an F dot a delta r, at least for that little piece. And so let me call it maybe a delta W, if you will, a little bit of work. And then we could play this same game again and again and again and again and again. And this hopefully looks like your second fundamental theorem of calculus. It is saying that the work total would be adding up all the little bit of work. And that means I'm going to add up all the little f's dot dr, and just to make sure that my force truly is a constant, I would say take the limit as the distance I pull it is equals to 0. And so I'm hoping that you could even do this without my help. Could you have taken what we learned in Physics 102, together with the math you learned in 150, reasoned out that here's a little bit of work, add up and you get the total amount of work, using this idea of an integral? What is this right there? Right, isn't that our second fundamental theorem of calculus? Isn't that the idea of an integral? And so what you're telling me, or maybe I'm telling you, but hopefully you will soon be telling me, that the work actually involves forces and distance and dot products and integrals when you put it all together. And that's the first section here of this chapter here. What is our equation? Now that we have trigonometry with dot products and calculus with integrals, what is our definition of work? And you can see that this equation is obviously a little bit, and maybe I should say a lot more advanced than you saw in your 102 class. Okay? And so that's why I put a box around it here. This is what I was getting at. Now we can have a varying force. And fortunately for both you and I know that many of you have been solving problems with work in your calculus class. Isn't that correct? And so a lot of you have been doing integrals, and you knew already, whether I had worked it out for you or not, you were told in your calculus class that if you integrate the force with respect to distance, you get the work. But here's what I want to ask yourself, or have you ask yourself. Could you have worked this out on your own? Or maybe a little easier question. Do you see how I was able to work it out? And we're going to keep asking that throughout the semester, because it's a skill that hopefully you will develop, because there's an interesting transition that takes place between Physics 121 this semester and Physics 122 next semester. You see, this semester, we always talk about it. We work it out for you. We don't next semester. One of the rudest awakenings students have is the start of next semester. It's late August, you come back from a long summer, and all of a sudden, boom, we start in the middle of the book, and it is not a simple chapter. One of the hardest chapters in the book is day one, and so students come back day one, and there's all this calculus that they don't give you the formulas, they just expect you to figure it out. Okay? And so that day is coming, but let's not push it too quickly. That's still 5 months away down the road here. But this is that idea. Could you reason through using your ideas from Physics 102 plus your ideas from your math class and put them together and come up with the formula on your own? A tough skill to develop, but one that the author is going to give you all semester to develop. And this, I think, is one of the biggest places and first places that he does it, and he does it well. And so that's why I take the extra time to work through and say, all right, be prepared to do this a lot of times, because you're going to be asked to add up like a lot of charges. A charge plus a charge plus a charge is an integral to get the total charge. You're going to be asked to do that with charges, with flux, and all kinds of other things as this goes on. So you'll see this same logic next chapter and the next chapter and the next chapter as we take and ask. Take your physics from 102, take your math from either your calculus or your trigonometry, and put them together. Okay? All right, well, like I said, here is a good first step. And part of the reason your author puts it there is because he says, well, let's actually give you a scenario where the force can change. If it was constant forces, these problems would be really simple. And in fact, they would just be like your Physics 102. So to go beyond a constant force, let's give a force that has some kind of varying to it. A good example of that are the use of springs. And so if you're not familiar with Hooke's law, let's repeat some of his observation. You probably noticed for the last few minutes here that I do have 3 springs that are hanging up here. Maybe to get things started here, I will take these 3 springs and I will put the same amount of weight on each of them. And the point of that is just to take the tension off the spring. Some of these are coiled up real tight and they snap against each other. So let's start right here. And so I'll make a little mark under each of them. Again, just like Hooke did. And say, okay, there's where they are. Let's add same amount of weight to each of them. All right? So I will put a weight on the red one, a weight on the white one, and a weight on the blue one. So let me make a little mark under here. Let me do it again. Oh, although I didn't give myself enough weights to do that, did I? I'm one shy. I'll have to move them around here. But let me put at least one on each of these for a moment. And I'll put one there, and I'll one there. And in fact, let me just steal one from here for a moment. Let me do the red one again. And then I'll do the white one here. And actually, maybe I'll just do the red one and the white one. Well, well, what the heck? I'll come over here. So let's see. First one got it down to here. Second one got it to there. Where does the third one bring it? To here. And then the fourth one right to here. And if we take a look at this pattern, we hopefully will see the same thing Hooke noticed. Starting with the idea that do you always get the same amount of force from one spring? Let's just talk about the red one. See, wasn't I hanging, did I mark the red one down here? I think I forgot to mark it. But when I put the red one on here, isn't this the extension of the spring? And every time I put a weight on there, wasn't it in equilibrium? So wasn't the net force equals to 0? And the point I'm getting at then is that I had a force when it was here, but when it here, wasn't there more force coming from the spring? And when it here, there was even more force coming from the spring? And when it was down here, there was even more still? And so that's what I mean by a varying force. The amount of force from a spring is not a constant number. It depends on how much you stretch the spring. If you only stretch it a little bit, you only get a little bit of force. You stretch it a lot, you get a lot of force. Notice also that every time I added one of these 500 grams, didn't it stretch by the same amount? Now, granted, the white one was the same amount for each 500, but it was a different amount than the red one. Same thing with the blue one. The blue one stretched the same amount every time I put a 500 on, but that number was different than the white one, which was different than the red one. And so if you were going to put that in mathematical form, you would say, well, the force does not equal a constant. That's very clear. In fact, you would say the force is then proportional to what I'll call x, how much I stretched it. And maybe I should pause here. Okay if I use an x for the symbol? Because I know I'm stretching it in the y direction. And so notice here that I'm not talking about the x direction or the y direction at this particular moment. I know I'm using an x. But what I mean by the x here is not the x direction. What I mean by the x is how much did I stretch the spring. Okay? And so there is the big step. A non-constant force. A force that does vary depending on how much you have stretched it. And of course, if it's proportional, that means you can write it as an equality if you put a constant there. You might call that the proportionality constant in a math class, right? What is that proportionality constant? We will call it the spring constant. Because notice then it has to do with how much force do you get when you stretch it a little bit. And in fact, that's why, and what I would say is different about these three springs, is that each of them, their force increased with the distance that you stretched it. But what was different about all of these is that there would be a different K value, a different constant of proportionality. I would have a K for the red one, which would be different than the K for the white one, which would be different for the K from the blue one, right? And so they each have their own spring constant. But they all follow this pattern, and hence it was discovered by Hooke, and so we call it Hooke's law. And so again, not a surprise, because I think you've seen this in your Physics 102. I suppose there's one more thing I should do before I put a box around Hooke's law here, because at this point, this is really just a discussion of the magnitude of the force. But every spring, didn't I stretch it down? And which way was the force from the spring? Up. And so to make the math make sense is I need to put a negative, which would be saying that the direction of the force is opposite of the direction of x. And so again, now x going down you can call positive or negative. Traditionally we have called down negative, so let me stick to that one first. But you can see here that in all of these, if I put in a negative value of x, I would have a negative here times a negative here, which would make the force a positive, right? And then likewise, I could have just as easily switched the convention and called down positive. That's fine. And so x would have been positive. But the force then would have been a positive times a negative, which would have made it a negative. So the force still would have been upward, but now upward we're labeling as a negative number. So again, nice little formula. That's why I'm going to put a box around it. And eventually we're going to put this together with this, of course, and see how those two play out together. But this is Hooke's law, that the force you get from a spring, and so let me just even put a little s down there just to remind myself, this is the force from a spring. It is proportional to how much did you stretch it. Oh, let's talk a little bit more about that proportionality constant. Which of these three would have the biggest proportionality constant? Now I'm going with the white. Why? Well, let's look at the last right here. Right here at this point, I had put 4 of these weights on it. The red one was way down here. The blue one was pretty close to it. That would way down here. Weren't all the springs lifting up by the same amount? Weren't they all holding the same weight? So I would say that every spring was lifting up with the same amount of weight, 4, which actually would come out to be, they were 500 each, so I guess that's 2 kilograms. And then whatever, 2 kilograms times 9.8 plus the hanger. But you put all that in there, all of them would be lifting up with the same amount of force. But obviously the white one had a smaller stretch to it. And that's because the K was the biggest. So the K, in this case, is the biggest. Let's look at the units. how would you describe the units to me for this value of K? Maybe if I wrote it this way, K is minus Fs over X. Isn't it newtons per meter? Right? How many newtons per meter do I get? Now, granted, there's a meter inside of the newton, so I could break this apart and cancel off the meters. But let's not. Let's leave it this way, because I think this gives us some insight. This gives us some insight into saying this is the units for the spring constant. The spring constant is really telling you really how stiff is the spring. If it is 100 newtons per meter, that means you would get 100 newtons if you stretched it 1 meter. What if I stretched it 2 meters? Well, I guess I'd get 200 newtons, right? And so the K value is again telling you the stiffness of it. How many newtons do you get for every meter that you stretched it? Notice it again is not telling you the force from the spring, because the force from the spring is not a constant. You don't always get 100 newtons of force from a spring that is a spring constant as 100 newtons per meter. The 100 newtons per meter says how much force would you get if you stretched it 1 meter. And so looking at this, clearly I don't have to stretch the white one very far to get the same amount of force as I needed for the red one. And so looking at all of these, that's why I would say the white one has the biggest spring constant. And which one would have the smallest? Yeah, the red one's a little bit smaller, it looks like, than the blue one. For the same logic, I've got to have a pretty big X multiplied then by a small K so that I can get enough force to lift up that 2 kilograms plus the hanger amount of weight. Right? And so there is our Hooke's law and the units, and hopefully an understanding of this spring constant. What do we mean by the spring constant? And so don't be surprised if many of our problems now involve springs, because they are very useful mechanically, but also they're a good one to use. They are the simplest non-constant force. I'm not going to say they're simple, but it's a non-constant force, and it's the simplest non-constant force I can get. And so that's why your author introduces Hooke's law right away when he introduces here the idea of work. He said, okay, this is the work, and this is what you would get from a varying spring. Now we can start to get to the main point here of this chapter, and that is this idea of energy. And here will be our definition. Our definition of energy will simply be the ability to do work. And so let's put some of this mathematics together here. What I just erased here on the board was that the work is the integral of f dot dr. Now, let me do this. Let me put net force right there for a moment. And so I'll do that side of the equation. But on the other side of the equation, which we had, I guess, earlier, and I erased it, we could say, well, the net force is the sum of all the individual forces, right? Wouldn't that be the same as adding up all the individual forces dotted with dr. Okay, so we could look at the net force, or we could say they're made up of individual pieces. Here's why. And this is, like I said, the real whole idea of talking about work is it's going to lead to conservation of energy here. Watch what happens here next. If I were to break this apart, I could have this integral of. And let's start listing all the forces that we're very familiar with. For example, one of them that we were familiar with is the force of gravity. What other forces are we familiar with? How about the force of friction? There's one we've done a lot with. What other forces have we worked with? Okay, normal forces. Let's talk about that for a little bit. What others? How about this new one with Hooke's law? How about a spring into the mix? There's one we haven't been using yet. You know, I heard somebody say the tensions on Earth. Okay. Why don't I just leave a stopping point and I'll just say others? Because at least here in chapter 7, your author really wants to focus on the gravity and the springs and the friction. The normal, as you'll see, is not a game changer in any way. So somebody said it and I'll put it there. But it also wants to leave the door open for other forces. But then again, that's probably a good place to at least pause for our discussion and say, okay, there would be the sum of all the forces. We probably don't have all of those forces for any one given problem. Sometimes we'll have, say, a spring, and sometimes we won't. Sometimes we'll have like tension hooked from a cable, and sometimes we won't. Sometimes we'll have other forces going into the next semester where we'll have electrical forces and magnetic forces and nuclear forces and other things going on. Friction. Oh, I'll just keep it simple right now and just talk about the friction we had in chapter 5, the either kinetic or static. So the solid-to-solid friction. Obviously, we could have also had the air resistant, but maybe a good discussion here just to begin with is the easier frictions, not the air resistance ones we just did in chapter 6. All right, so I'm hoping that this side of the equation makes sense. Let's look at then this side of the equation. I like this equation here because now I can use Newton's second law and replace net force with mass times acceleration. And so there is my two sides of the equation. So let's break this down piece by piece. Let's start with this first one right here. Let's look at the integral of the gravitational force times the distance traveled. What would that equal? Well, help me out with gravitational force. How would you mathematically describe the gravitational force? Maybe I'll put a grid over here. Why don't we stick to the traditional one here for just a second? And so I'm going to call up positive in the y direction. Right. I would say the magnitude of this one right here would be written as mg in the negative j hat direction, right? Fair enough? Well, let me take a dot product, dot. And then this, what was this again?
The magnitude of the distance traveled.
Okay, this is the vector that it traveled. Now I'm being a little abstract here at the beginning. The object may not go straight down. What if the object went off at an angle like that? Yeah, wouldn't I describe that as maybe a movement in the x direction I hat plus a movement in the y direction? In fact, couldn't any movement kind of be described by that? At any given moment, it's moving a little bit in the x and a little bit in the y, even if it followed a curved path? Okay. Here's what's nice about that. That becomes actually two integrals. It becomes a minus an mg, and then I would have this I hat dot this j hat, or j hat dot I hat, I suppose, dx. And then the other one here would be a minus an mg j hat dotted with a dy j hat. And again, I would say, again, more mathematics than you certainly probably did in your last physics course. But again, not out of the realm of possibilities. And in fact, when we're all said and done, it's going to end up with an equation that I think you're already familiar with. But it's nice to see it at a higher mathematical level. What would you say here about this dot product? Yeah, why 0? They're 90 degrees, aren't they? Right? You are really saying, take this, which is clearly in the y direction, and dot it with this, which is how far did it move in the x direction? Well, going way back to the beginning of this lecture, the amount of work depends on how much of this force is in the direction it moved, which would be 0, exactly. And so this is 0. If you like, there's your dot product, right? This is the cosine of 90 degrees. What is the angle between a j hat and a I hat? Doesn't an I hat mean the point in the x direction? And doesn't a j hat mean point in the y direction? So isn't the angle between them 90 degrees? And so there's my dot product. And so simply put here, this, which we would call the work done by gravity, does not involve anything to do with how far does the object move in the x direction. And that kind of makes sense. I bet you even remember that from your Physics 102 class, talking about that. If I had an object like this calculator, and I move it from here over to here, how much work do I do? Well, none. The work of gravity is this way. You've got to lift it either up or let it go down for there to be work. There's got to be a movement in the y direction. And that's exactly what the math is giving us. It is telling us that there's no work being done. Those two are at right angles. But here, what would you say about these two? Especially just looking at the j hats. What would you say about a j hat dot a j hat? Well, remember how we did dot products, right? It was the magnitude of the first times the magnitude of the second times the cosine of the angle between them. So what's the magnitude of this one? 1. What's the magnitude of that one? 1. What's the angle between them? And so a j dot a j would be a definite 1. Maybe I should have done that much detail here, right? J hat dot I hat would be the magnitude of the first times the magnitude of the second times cosine of the angle between them. And that would be 0. And so here is I get a number, and here I don't get a number. So it looks like what I have then, so far, is a negative mg dy. There's my first integral there for today. And it's a very easy integral, right? If I say let the object start at some initial position and then finish at some final position, then I can factor out the negative mg, and then just I have an integral of dy, and then that would be final and initial. And maybe I've run out of room here, so I'll kind of jump over to here. But working on this first integral, I get the same formula, maybe with a little more advanced mathematics, but the same formula that you guys saw in Physics 102, where you would say then you get a minus mg and then y final minus y initial. Isn't that the height? And so I bet in 102 you learned what is the equation for gravitational potential energy? mgh, sound familiar? And we're essentially doing the same thing. But, as you can see, with the potential of having a lot more pieces to our puzzle than just gravitational potential energy here. But that first term then is going to be referred to as its gravitational potential energy. I like to separate it into its two pieces and say negative mgy final plus mgy initial. And so you might say, here's this object, this part of it right here is what I would call its initial potential energy. And this part right here would be its final potential energy. And so other than I got there in a more mathematical way than you probably saw in Physics 102, don't I really have the same thing, the potential energy, mgh. But instead of using h, I'm going to go ahead and use y. And notice the nice part about working it out from here, besides we're going to have the potential for doing it for other forces, but it does show me something very important here, and it was the fact that this one came out to be 0. The gravitational potential energy depends only on up or down. Okay? By the way, hopefully you noticed along the derivation here, something that I did. Didn't we call down negative right there? So if you ever want to use the equation mgh, or now we'll start calling it mgy, in your equation, you need to make sure you call down negative and therefore up positive. Fair enough? Because this equation would only be valid if that step is here, which is only valid if I call up positive and up negative. Maybe that's so obvious I don't need to mention it, although I really want to mention it for the other side of the coin. Did I define where y equals 0? I really haven't, have I? That's going to become really nice because, like any problem, what if we called, say, the starting point or the ending point y equals to 0? What would that do to our equation? It would make one of these go away. So we're going to take advantage of that and remember that, hey, we're going to head and use this equation all we want, but once we start using it, we need to remember where it came from, right? That whole idea of we have the freedom of choice, but once chosen, it has power over us. And so if I'm going to go ahead and choose to use this equation, the same one you've been doing in 102, MGH, okay, there's a condition on that, and the condition is that I have to call up positive and down negative. Okay, that's fine. I like that choice, actually. I don't feel like that's much of a hindrance. But the neat thing about it is I can pick y equals to 0 still anywhere I want. That has not been chosen for me yet. And so I would encourage you to remember that. You can make the problems a lot simpler on yourself. Also, it will help you when we deal with springs here in a second. So let's talk about the next one here. Why don't I actually then jump over to this term? And maybe I'll put a box around this one so I don't accidentally erase it. I'm going to need a lot of space here. But let's look at the second integral. Let's look at the spring. Let's grab that one for a moment. Now, this is new to you. What is the equation from a spring? Well, we just did it. We called it Hooke's law. And so let's put that in here. This is the integral of minus kx, right? What direction is the force from a spring? Yeah, it's opposite of the displacement. So let's be real careful here. Does this x mean horizontal? No, right? And so back over here, when we were dealing with gravity, the x and the y, what did we mean by those? Well, we definitely meant x was horizontal and y was vertical. But when we derive this for the spring, that's not quite what we mean here by x. So keep that in mind as we put these two equations together. I'm going to continue to write it as an x, but that can get a little confusing if you don't really understand what was behind it. So I want to point this out. I'm writing as an x, but that does not mean the x direction. As you can see, these springs were laid out in a vertical direction. And so what I would really mean by x in here is really y. Fair enough? And if I took these same springs and I laid them out horizontally, then I would really mean x is horizontal. But I could also lay out the springs along an incline or something. And then what I would mean by x is along the incline. That's just a long way of saying be careful. The reason we go through this derivation is so you'll see where they came from. You have to understand where these things came from. Again, if all you do is take the equations at the end and think you're going to walk into the test and take that equation and plug that into there, you're going to miss a lot. You'll get enough partial credit that you'll do okay and get an okay grade and transfer to an okay school. But it's far beyond plug and chug here. There is mean and deep understanding behind them. And it's the whole reason things fall apart and break and prototypes don't work and airplanes crash is somebody just overlooks the obvious. It's like, really, did you not understand where that came from? You guys into programming, you see that a lot also where, you know, well, I don't want to type all that code. I got this program over here. What I can do is just copy and paste all that code. Yeah. But when you start mixing and matching, if you don't really know what all that code is saying and you don't know how these pieces are connected together, it can really foul things up. Yeah. And it doesn't take much to really foul something up. And this is a good place on that. I think when you really understand where these came from, these problems are going to look trivially easy to you. And you're going to walk in when we take the test and just blow it away. But if you don't understand where they came from, it just becomes I don't know, guess game. And so this is just one of those places that this can occur. And so I'll say it again. What does x mean here? Not necessarily horizontal. X means how much this spring is stretched. Oh, by the way, I should have even pointed out, it could also be compressing the spring. I don't really have the ability to demonstrate it with this spring, but if you could imagine a giant spring that is maybe mounted against this table and going like this, And if I were to grab it right here and then pull it this way, I would be stretching it. And since I pulled it this way, I think you would agree the force is opposite of it, right? But what would happen if instead of me pulling on it, I compressed the spring? It would push this way. So I would compress it that way, but it would push back opposite. So the little equation still works. And I should emphasize then that Hooke's law right here is valid for stretching as well as compressing. And so what we like to say is this little x represents how far the spring is either stretched or compressed from its natural length. Okay? And so I'm going to put that equation in here. Which is kind of nice, because that means then if I have a spring, I can either stretch it or compress it. But I am doing something when I put in that equation. Where does x equal to 0? The natural length of the spring. Hooke's law is useful, but Hooke's law is also defining where x equals to 0. Fair enough? Don't overlook that when you start working on the problems. And that's kind of the opposite of what we just had for gravity. When we worked this one out for gravity, using the end result right here meant that we have to call up positive and down negative, but we can pick y equal to 0 wherever we want. Using this equation for Hooke's law means we have to use x equals to 0 at the natural length of the spring. But we could call left or right positive or negative, or up or down positive or negative, or along the incline. So this one is not choosing the direction, but it is choosing the origin. Whereas this one here is choosing the direction, but not the origin. So keep that in mind as I do the problems. Because we won't be surprised. I'm going to pull out this equation, and once I do, I need to realize, I know that I have to call up positive. I can still pick y equal to 0 wherever I want. And then when I start using this result, which we haven't worked out yet, I will notice right away that, hey, I must use x equals to 0 at the natural length of the spring. And that's so easy to forget unless you've gone through these individual steps and worked it out what they mean. And so you'll see that as we get into some problems here. So again, my first step is to put the force from a spring as minus kx. And as you guys correctly pointed out, I'm going to put a little I hat here. But again, that does not mean the real horizontal direction. The x in that equation means the direction the spring is either compressed or stretched. And x equals to 0 was the natural length. So be careful with that. Then I will say I am going to move the spring. Usually when we move the spring, we only either stretch it or compress it. But I guess I could do this. Don't ask me why I would, but I could. I could say, again, maybe there's a spring right here. And the spring comes to right here. And so what I could do is stretch it. So I would say at that point I am moving in the x direction. Then when I get right here, I could kind of lift the spring up in kind of an arc shape. So I would say I'm moving in the y direction, but I'm not stretching or compressing the spring. Which, just like we had back here for gravity, isn't a big surprise. When you take this dot product, you will hopefully get two integrals. You get a minus kx, and here I would get an I hat dot an I hat dx. And the other one would be the integral of minus kx I hat dot j hat dy. And what's this right there? Yeah, that's the same discussion we had a few moments ago. That is 0. That's because it's the magnitude of the first times the magnitude of the second times the cosine of the angle between them. Okay? And so that's going to be 0. And that hopefully makes sense, right? Imagine a spring. I take the spring and I stretch it. That's going to be this part of it. But this part, where I kind of lift it up, isn't giving me any work. I'm not stretching the spring anymore. Oh, now you may say that it weighs something, so you're lifting it up because of gravity. Okay, but that's not from the spring. That's this one. That's the gravitational potential energy. And so that one is going to go to 0. So just like we saw for the force of gravity, there's components that matter. And then this one's kind of nice because, again, just like last time, this would be magnitude of the first times the magnitude of the second times the cosine of the angle between them. And cosine of 0 is 1. And so what I end up with is an integral of minus kx dx. Unfortunately, that's a very easy integral to do. If I start with the spring at some initial spot and stretch it to some final spot, I get a negative 1/2 kx final squared minus a negative, which maybe I should just call plus, a 1/2 kx initial squared. And so I actually will, since that's what I did over here on this step. And so there would be the stretching or compressing of the spring. So, because remember, it would be the same formula whether I stretch or compress. And so there is what we're going to call the elastic energy from a spring. And this is the one that, did you guys see this one in 102? This might be new. I know you definitely saw this one, right? This is the gravitational potential energy. But this, then, same idea, we'll call it an energy, and a potential energy, but we'll call it an elastic energy, the stretching or the compressing of some kind of object. And so we've got each of those. All right, so let's see. So far we've dealt with that one. I'll underline it. And we've dealt with that one. I'll underline it. Let's look at some other ones here. Maybe these are even a little easier. Let's look at that one there. And maybe I'll try to squeeze some in over here so we can have everything on the board in one time. But that one is the force of friction. So this would be the integral of F of friction dot dr. And earlier I said, like maybe I should put a dotted line, that let's only deal with solid to solid friction here to begin with. Even though we just got done with chapter 6, which took us beyond solid to solid friction and we had air resistance. But back in chapter 5, we had static and kinetic friction. All right? Let's say it was static for a moment. And so I guess I got two options. One option is this could be an integral of static friction dotted with the distance it moves. And the other option is it can be an integral of the kinetic friction dotted with the distance it moves. All right, well, let's start with the static. What would I get here for the work done? And remember, if it's static friction, it's not moving. Or I should say it's not sliding. So how far would it slide? Yeah, and so it's just going to be 0, right? There is no movement going on. The work has to be force times distance. So if we have static friction involved, there is a zero term from that one. Keep that in mind. Obviously, most of the time then, if we want anything to show up, it's going to be in this term, right? And of course, as you are familiar with, isn't this the coefficient of kinetic friction times the normal? Isn't that the magnitude of the kinetic friction? And what direction is it, by the way?
Negative.
Okay, it's opposite of the direction it moves. So maybe I could write it as magnitude of the first vector times magnitude of the second times cosine of 180 degrees. And I would say we already really did this one earlier today. We just said force times distance, and we had that cosine of 180 degrees. So this comes out to be negative. And then I've got an integral of mu k n dr. And one thing was really nice about the kinetic friction is that term was a constant, so this is minus a mu k n r. And I'll put a box around that, and maybe even a box around that, since it's one or the other. It either is not sliding, and so the amount of friction is zero, or we got that number. Okay, so it looks like we've covered 3 of these integrals so far. All right, so I've got that one, I got that one, I got that one. How about this one here? And that one's fortunately a pretty easy one. Normal force. Well, by definition, isn't the normal force perpendicular to the surface? So if I take the integral of the normal force dot dr, well, let's see what I would have. Here's my object sitting on a table. So let's see. If the object moves, say, to the right, isn't the normal force up? So how much work would be done there? 0. If the object moves to the left, how much work is done? 0. If the object is moved maybe up at an angle, which of course means it's not touching the table anymore, so what happens to the normal force? 0. Can you think of any time it would not be 0? Yeah, I can't either. All right. So that's probably the easiest one. And it's probably why your author doesn't even include it when you watch his derivation. He doesn't even say, hey, let's look at the normal force. I think in the words of the textbook, he just says, oh yeah, the work done by the normal force is 0, and then he moves on. But one of you said I should put all the forces up there, and one of you said the normal force, so I wanted to make sure I included everything you said. And including then other forces, which there's nothing really I can do with that integral, just there's other forces, depends what they are. So I'll leave that one just as it is. It's the integral of other forces. So I think I've pretty much covered this side of the equation, where I've done that one, and I've done that one. I showed that one is 0. I've done that one, and that one I'm just going to leave alone. So let's do the other side of the equation. What's this one? What is the integral of ma dot dr? Well, maybe I'll write it this way. M, that wouldn't there be an acceleration in the x direction and an acceleration in the y direction? And then if the object moves, dr. It may move a little bit in the x and a little bit in the y. Okay, so maybe I'll write it as dx with an I hat and dy with a j hat. Okay, so there's my multiplication. And for some of you, it's probably the first time you've done this, but I know you've done FOIL before. I mean, I guess when I multiply this out, I'm thinking I should have 4 terms. This would be mass times the acceleration in the x direction I hat, dotted with I hat dx. That would be the first term, let's say. But since we've done the second term a few times, can I just save a little bit of work? What would I get when I took the first term here and the last term here? Which in FOIL, you'd call them the outer. Right, you'd get 0. Why would you get 0 here? Right, the I and j that we've been doing. And then continuing with our FOIL, we would have the inner ones. What would you get here? 0 for the same reason, right? You would have an I hat and a j hat. So what we call the cross terms, the O and the I in the FOIL, they're going to go away. And the only thing that's going to be left here is this last term, which would be then another integral, which would be mass times acceleration in the y direction, and then it'll be a j hat with dotted with a j hat dy. So the cross terms go away, and we see what we saw before. What would you call I hat dot I hat? 1. And what would you call j hat dot j hat? 1. All right, so you guys are getting good at those. Good. I'm glad we went through all this. And so these two integrals simplify. In fact, they're kind of looking the same to me. One, however, has an x component. And the other has a y component. See if I gave myself just enough room to squeeze it in here. Then we can put the grand finale here. But what about this one here? This is the integral of m Isn't acceleration the derivative of velocity? So in place of acceleration, I'm going to put the derivative of velocity. And of course, I'm going to do the same thing for the other term, m dv sub y dt dy. And let me regroup things together. What would you call that? dx dt is what? Isn't that the velocity? So would it be okay if I write velocity in the x direction? dy dx? Same thing here. Velocity in the y direction, dy. Because when I integrate this from, say, some initial velocity in the x direction to some final velocity in the x direction, doesn't this become 1/2 m vx squared evaluated from its initial to its final speed? And over here, don't I get a 1/2 m vy squared evaluated from some initial y speed to some final y speed? And although I have two terms, wouldn't that mean I have a 1/2 m vx final squared plus Vy final squared combined together minus 1/2 m Vy initial squared and Vx initial squared. And when you put x's and y's together, isn't that the total speed? So doesn't this come out to be 1/2 m v final squared minus 1/2 m v initial squared? I bet this looks familiar. Does this look familiar to anybody? What'd you call this? Right, this is the kinetic energy that you saw in 102. Now granted, I don't think you went through this integral to get there. In fact, in physics 102, you were either just given the equation that says, hey, this is the equation for kinetic energy, 1/2 mv squared, and told that it would be proven to you later on. Or once in a while, we'll show how it works out if you have a constant force. But I wanted you to see, with calculus, you get the same answer whether you have a constant force or not. None of what we did involved a constant force. And so that is the equation for kinetic energy, 1/2 mv squared. And this is where it comes from. It comes from way back here. The first thing we did was a substitution of Newton's second law. And then the next thing we did was to separate it out into its components. And the big step really was to change acceleration into its derivative so that we can do a change of variables here, and then we can do our integral. And we get the 1/2 mv squared. All right, well, I knew this would take a long time. And I hope I didn't lose the goal in all of this. But we have now done every single term in this equation. And let's see what it's telling us. Yeah.
I'm just wondering how you got rid of the x and y components. So there's like the I hats and the j hats above it right there. Well, yeah, all of those. And then now it's just 1/2 mv squared final minus 1/2. Like, I'm just wondering how come there's no more x and y.
Well, because I have a final in the x and a final in the y. And if I put those together, that is the total final speed. So x and y components together is final speed. Yeah. Good. All right, so like I said, a lot of math here today. But that aside, let's look at the grand finale of what we got here. And as you'll see, as you start working out the problems, it's going to be important you come back and look at where did all these come from. But I think at this point, it's good just to see, why did we do all this? What is the results that we have? And so let's start with this first term right here. It's still on the board right here. This is the integral we got. This is a minus mgy final plus mgy initial. Fair enough? Friction. The friction one is this one way over here. Okay, let's write that one. That is a minus the coefficient of friction times the normal times r. That's if it's kinetic friction. It would 0 otherwise. Okay. Normal force, well, we just argued that that one was 0. The spring. The spring integral is what we did here, so let me write that one. That's minus 1/2 kx final squared plus 1/2 kx initial squared. Others. I didn't actually do the integral, I just left it there that we could do the integral because I don't want to specify what the other forces are. There'll be some problems where we have forces that are more than just a gravity or a spring or friction, but that'll be most of our problems. So why don't I do this? Why don't I just say this right here is the work done by other forces. And then if I have a problem that has other forces like the tension in a cable or some kind of an electric or magnetic force, which we wouldn't do any electric and magnetic forces this semester, but next semester, let me just leave that door open for other forces. And we've got plenty to work with for our starting. But that would be the work, and that was this whole equation. So this is the work done by gravity, this is the work done by friction, the work done by the normal force is 0, this is the work from the spring, this is the work by the other forces, if there are any other forces. And then this one, which, where is the, last one right here. And then that is what we're going to call the kinetic energy, 1/2 mv final squared minus 1/2 mv initial squared. And I know it looks pretty lengthy here, so let's rearrange it and put it in a form that we can kind of commit to memory here. And let's do this. Everything that has a negative, let's move to the other side of the equation, so that everything is positive. There's no negative signs left in this equation when I'm done. Okay, so let's see what that would be. I would leave this one on this side of the equation, but I'll take that one and I'll put it over here. This one I'll put over here on this side of the equation. So now it'll become positive. This spring, I'll leave the initial one. Oops, I think I messed up. Did I move the wrong one? I did. Let me try that again. The initial is the positive. The final was the negative. Okay. And then that one was negative, right? Moved over there. Okay, good. Then this one, the initial is the positive, but the final is negative, so I'll move it to the other side. This one, I'll just leave it alone. And then over here, I will leave the final on that side. And over here, I will put the initial. You notice anything yet? Did you notice everything that has initial is on this side? And everything that has final is on this side? They're all positives. Well, what is this really saying then? Well, the initial energy here plus the initial energy here plus any, I'll call added energies, which I'll just leave that one alone there, plus the initial kinetic energy. Isn't this over here what I would call the initial energy of the whole system? Right? This is all the energies added together. This is the energy I get because of gravity. We'll call this gravitational potential energy. This is the energy I get from the spring. I will call this then the initial elastic energy. This is the energy of motion. This is the initial kinetic energy. So let me call all of this the initial energy. What is the initial energy then equal to after something happens? The sum of all the final energies, right? This is the energy that it has with gravity. This is the energy it has because of the friction, the rubbing that's going on. We'll call that heat energy. Oh, this is the energy in the spring now, at the end of it. This is the final elastic energy. This is the energy that has to do with motion. And so if we take all of that hard work that we just did and call each term an energy term, what we have is conservation of energy. What is it saying? The energy you start with is equal to the energy you ended with. And that was a huge background and probably looking a lot more complicated than you saw in Physics 102. But trust me, it's not any more complicated. Yes, it's got some integrals behind them. The good news is most of these integrals I already did for you. So you won't have to repeat them. Hopefully they made sense, and the reason I went through them is so you can remember what each term means, but chances are you won't have to do the integral again. Now, over here under others, I haven't actually done the integral. So we come across anything like that, you probably are going to have to do the integrals. But the other integrals I've already done, so I would encourage you not to redo those integrals, but to go through this and look at it and see what we're trying to say here. What we're trying to say here is the energy you start with is equal to the energy you end with. Most of you, probably coming from Physics 102, did the simplest cases of all. You probably looked with gravitational potential energy and kinetic energy. You probably didn't deal much with a spring, if at all. You probably didn't deal with other forces. You probably also didn't even deal with friction. Maybe you did there a little bit. But you did what I would call the first step, the simple version of conservation of energy. I would also say it's probably a good idea that I don't think you derived the concept behind conservation of energy, coming from the idea of doing the integral. But I'm hoping that now that you see it in its fuller detail, that it'll make the problems a lot more simpler. So, I put a box around this. Of course, that makes it look easy, but please remember, that is really this. So there are four terms here. Gravitational potential energy, elastic energy, any other additional energies that are not covered with these other ones, and the kinetic energy has to equal to what? Potential energy, heat energy, elastic potential energy, and kinetic energy. And if you can keep that in mind, you will be able to answer every single question in chapters 7 and 8. And so, do you want the answers to all the homework problems in chapters 7 and 8? There it is, right there. So, there's 7 and 8. Let's not forget 5 and 6. There's 5 and 6. Together, that is the answer to every question on the test. And of course, it's easy to say that way. It's not so easy to solve the problems, but that's what the author and what I am after here is this whole idea of conservation of energy. There's a couple more little things we should mention just to kind of wrap up this whole idea of energy in the time that we have available, and then when we come back on Wednesday, we'll just do example after example after example, starting in chapter 7 and then jumping into 8. But this was that big grand finale that I was trying to talk about here, that the energy you start with is equaling to the energy you work with, end with. Now, keeping that in mind, what are some of these other little things in mind? Well, let me start with one, which is, do you remember at the beginning of this lecture, I put a diagram on the board that said if we talk about energy and we come up with this concept of conservation of energy, we should be able to solve problems to get to velocity using a different technique than the technique of forces. So let me put that diagram back on the board here. Here's the diagram on the board. We had position, velocity, acceleration. These three things were connected. Then we had net force, and then I had the sum of the forces. And up until we started this chapter, I said, if you wanted to know the velocity, say, of a falling object, and so I take my pen, I hold it out, I let it go, and as it falls, we would have probably looked at the force of gravity and maybe even air resistance. We would have added them together to get the net force. From there, we would have taken the net force divided by its mass, would have got the acceleration. We would integrate the acceleration to get the velocity. Fair enough? But I said there is a second approach, and at times, and this is one case, where it would be a lot easier to do this in terms of energy. And so let's come back here. What I can do is when I hold up this pin to drop it, I can say, doesn't it have some gravitational potential energy? Now, for this simple case, there's no point in talking about that term. There's no other forces going on. And if I'm just holding it at rest, the initial speed would be 0. And so as you look at this equation, you would say something to the effect of, okay, I know that term, and I know that one, and that one. Okay, so I know all these. And then look at the other side of the equation. If I just let it fall, and it falls all the way to the ground, then don't I know its height here? So I know that term. And we're ignoring any friction, so that term won't count here. There's no spring, so that term wouldn't count here for this case. And then I can get the final speed. And that was what this little diagram was trying to show you here, is that without going through Newton's second law, I could get the speed of a falling object. But that wasn't the only thing in this diagram. This diagram also said you can get forces if you know the energy term. But let's take a quick look at that before we go too much further here and say, okay, well, watch this for a moment. We said that if you integrated the force and the distance here, you would then get the work. Now, I don't know if you kind of caught this, but a lot of these equations I left on this side, and then I brought them over to here. Well, we'll get back to that minus sign in just a second here. But let's say that I already know the work, but I'm after the force. For this last hour, we've been going the other way around. We've been saying, if I know the force, you can get the work. How can I solve this for force? Well, doesn't this really mean force in the x direction and force in the y direction? Dotted with a movement in the x direction and a movement in the y direction. And so let me take the dot product again. And now that you guys are getting good with the I hats and the j hats, I'll do the FOIL. But hopefully we don't have to do all 4 terms, right? Because the first term would give me fx dx. That would be the first term. As you guys pointed out, this term right here would be 0. These two multiplied together would be 0. This one would be then the integral of fy dy. Fair enough? Now, I'm going to ask again, doing the opposite of what we just did for the last hour. The last hour, I gave you the forces. We knew the forces. We did the integral. But what about the other way around? What if we already knew the equations for the work? How would I get fx by itself? How do I undo an integral?
Could you take the derivative of the work?
Right, take the derivative, exactly. So I'm just asking you a little bit about your math, a little bit of your calculus. I'll say it again, I've been saying it all day long because there's a lot of math in this beginning part here. The result, when we're all done, fortunately, you don't have to go back and do all the math. But it is all that math in here that is the difference between the 102 and the 121 here, and the meaning behind all those. But watch this. If I were to take the derivative, and maybe I'll just take the whole equation and say, let's take the derivative with respect to x. Doesn't this derivative undo the integral? So doesn't this give me Fx? Here's an interesting one. What does this really mean? This says add up as you move along the y direction. And this is asking, how does that vary along the x direction?
0.
And I'd say it doesn't. It is 0. And of course, then I would have the derivative with respect to x of the work.
What if you just have like a number? It's going to give you like 0.
Well, yeah, but so you can't take a derivative of a number. You can take a derivative of a function. So you have to have the equation for how the work changes with, say, position. Yeah, for this to make any sense. Yeah. And so there would be my force, at least in the x direction. How would I get my force in the y direction?
Take the derivative with respect to y.
Exactly. If I were then to take the derivative with respect to y of my work, I would get the y component. And so again, that's what I was saying here, although I must admit, I put in this little box energy, so this is really negative of the energy, and this is negative of the energy, since I was putting these on the other side of the equation before I defined them on energy. So the energy is the negative then of the work in that matter. But my point is that most of the time when we solve the problems, and again you'll see this on Wednesday, I will take the energies, I will add them up, and from that I will get the speed. However, there will be times where the question is asking you to find the force. So if I take the derivative, I will get the force. Let me try this with a couple of them. Let's look at the one, and bummer, I guess I've erased all the energies, but the work right here, wasn't there a gravitational one right here? And if you remember here, then we had a formula that said the work, and maybe, bummer since I'm low on time, I'll just say work being the negative of the energy, we got then a negative mgy. And so that is that number, that bummer, I had two pieces here. But in the interest of time, watch what happens if I take the derivative of this with respect to x of a negative mgy. What do I get? 0. So how much force do I have in the x direction from the gravity? 0, right? How much force do I get in the y direction? Negative mg. If I do that with the potential energy, which again I kind of shortchanged you from showing you the negative of the work is the potential, but I want to make sure I finish here. But if I take the derivative with respect to x of the negative of 1/2 kx squared, and if I take the derivative with respect to y of the negative 1/2 kx squared, and so the kx squared, which again was over on that board and I erased it, but I think you can still see it here in this form. This is the energy we said, which is from the spring. And so if I take the derivative with respect to x, what do I get? minus kx. Wasn't that our argument? That is the force from a spring. So if I didn't know that, but I knew the energy from the spring, I could take the derivative to get its force. And then likewise, what would be the derivative of this one? 0. There's no y's in there. And so again, the spring only gives me a force when I compress it and I stretch it the x direction, not the y direction. And so now, I'm hoping you see what this diagram was trying to say. I can either use energies to fill in my knowns and find the final speed, or if I know energies, I can take derivatives of that to get forces. And those are going to be the two big steps that we're going to take. There's a few other little things to talk about in this chapter, but let me just, as we're out of time here, point out this is the main point. Conservation of energy. If you take all the energies before something happens, it will then equal to all the energies after something happens. That's the nice thing about conservation of energy. And I think you have seen it there in 102. All right, well, I know that was a lot to digest in one day.